Hey there, and welcome. Think about it. Pretty much everything around us is in motion. You've got planets orbiting the sun, cars on the highway, even the air we breathe. But how do we actually talk about all that movement? In a way that makes sense? Well, today we're going to unpack the language of physics that describes how things move. Let's get right into it.
Okay, picture this. You're driving along and a big truck is right in front of you. How much space should you leave? We all ask ourselves this, right? But is there a real solid answer, and does it change depending on how fast you're going? This isn't just about being a safe driver, it's a pure physics problem.
So to figure out that truck question, and a whole lot more, we need to wrap our heads around a few key ideas. These are the tools scientists use to describe any kind of motion. And honestly, once you get them, you're going to see the world a little differently.
So, first things first, where do we even start? Well, before we can say something is moving, we have to ask a really simple question. Moving compared to what? And that brings us to our first absolutely crucial concept, the reference point.
A reference point is basically the "you are here" dot on a map. Without that starting point, that origin, words like forward, back, up, or down just don't mean anything. If your position changes relative to that fixed spot, you are officially in motion. It's really that simple.
All right, now here's where things start to get really interesting. And this is a big one, a spot where a lot of people get tangled up. We tend to use the words distance and displacement like they're the same thing. In everyday life, that's fine, but in physics, they are two totally different concepts.
Okay, so distance is easy. Think of it like the odometer in your car. It just adds up every single step, every single mile you travel. It's the total length of the path you took, and it couldn't care less which direction you were heading. Let's make this real with an example. Check out this athlete. She starts at the origin, which we'll call O, and runs 100 meters all the way to point A. Then she turns right around and runs 60 meters back, ending up at point B. To find the distance she traveled, we have to trace her entire journey. And the math is super simple, right? We just add it all up. She ran 100 meters out, plus the 60 meters she ran back. That gives us a total distance of 160 meters. Straightforward.
But now, let's talk about displacement. Displacement is completely different. It does not care about the long, scenic route you took. Displacement only cares about two things. Where did you start and where did you end? That's it. It's the shortest, straight-line path from your start to your finish.
So let's go back to our athlete. Remember, she started at O, and her final position is B. For displacement, we just draw a straight arrow from O to B. All that extra running she did out to point A and back, for displacement, it's like it never even happened.
And here's where you really see the difference. Her final spot is at the 40-meter mark. She started at 0, so her displacement is just 40 meters. Now compare that to the 160 meters of distance she actually ran. Big difference, right?
So let's lock this in. Distance, that's the total ground you covered, your odometer reading, and it's always a positive number. Displacement, that's just the change from start to finish, the shortcut. It can be positive, negative, or even 0 if you end up back where you started. And it always includes direction. So now that we've got that down, we can build on it. Because this very same idea, the total path versus the net change, is exactly what separates speed from velocity. Let's use a new example to make this super clear. We've got a swimmer in a 25-meter pool. He swims from one end to the other, touches the wall, and swims right back to where he began. And that whole trip takes him exactly 50 seconds. First, let's figure out his average speed. Well, speed uses distance. So he went 25 meters there and 25 meters back. That's a total distance of 50 meters. We just divide that by his time, 50 seconds, and we get an average speed of 1 meter per second. Totally makes sense. Okay, but what about his average velocity? Now remember, velocity is the tricky one. It's based on displacement, not distance. So, what do you think? Any guesses? Yup, it's 0. A big, fat 0. Now that might feel weird, right? How can his average velocity be 0? We know he was moving the whole time. It all comes back to displacement. He started at one end of the pool, and he finished at the exact same spot. His starting point and his ending point are the same. That means his net change in position, his displacement, is 0. And 0 meters divided by 50 seconds is still 0 meters per second. Okay, so we've nailed down speed and velocity. Let's add the final, crucial piece to this whole puzzle, and it's going to bring us right back to that truck we started with. Let's talk about acceleration. Put simply, acceleration is just any change in velocity. And here's the key. Since velocity includes direction, acceleration isn't just about speeding up. It's any change in your speed or a change in your direction. Taking a turn at a constant speed, that's acceleration.
And it's all about direction. When you hit the gas and speed up, your acceleration is pointing in the same direction you're moving. But when you hit the brakes, just like our truck, your velocity is still pointing forward, but your acceleration is pointing backward, working against it. That's all slowing down is. It's an acceleration in the opposite direction. So, reference points, distance, displacement, speed, velocity, acceleration, we've covered a lot. But why is it so important to know all this stuff? Well, because these few concepts are the building blocks for describing literally everything that moves, from a person taking a walk to a rocket launching into space.
Let me leave you with one last question to bring it all home. Think about your car's fuel efficiency. You know, miles per gallon. What does your engine actually care about? Does it care about the long, winding road you took to get to your destination, your total distance? Or does it only care about the straight-line shortcut from your house to the store, your displacement? It's something to think about next time you're filling up the tank. Thanks for joining me.